Good evening. So we are approaching the end of the course. Today we will study the last type of integral in this class, namely the surface integral. As I mentioned last time, most students will find this topic quite difficult because it's toward the end of the class. In my opinion, it's not overly difficult, and if you make an analogy with the line integrals we learned so far, things are much easier. The difficulty usually comes from the fact that it's the last topic, and at this point lots of material accumulates over the semester. And there is another piece which adds to the complexity. When you actually set up the integral, in my opinion, the surface integral requires a little bit of care, far more care, let's say, than the other integrals when you actually set it up. It all boils down to plugging in the components in the right place, basically. But you really have to force yourself to be patient and make sure, first of all, you understand how you define the integral, what it tries to measure, and how you set it up, and then set it up slowly before you actually get ready to compute it. Just like in the case of line integrals, so in the case of line integrals, remember we had two types of line integrals, one over scalar fields, right? So the function to integrate is a scalar function or a function of several variables, or over vector fields, in which the function to integrate is actually a vector field, right, with three components denoted like we did it before by three functions p, q, r. So these tools, this surface integral is basically defined primarily for just for the three-dimensional spaces. Now, over a scalar field, I'm gonna refer back in terms of the meaning of it to the density-like function. So remember we talked about the center of mass, but pretty much any density type function. In the case of a center of mass, let's say you have a piece of the material in the shape of a generic surface. And then in this chapter, remember we identify or we describe a surface via a parametric surface, right? A vector function depending on two parameters. So let's say the surface is given by r of uv with the components x of uv, y of uv, and then z of uv, where d is the parameter domain. For u and v. And let's say we want to find eventually the center of mass, or the total mass, let's say, for this piece of material. So in that case, the function, which we will integrate eventually, let's say f of x, y, z denotes the density at point x, y, z on this piece of material. And to compute the total mass at that point, that means we're going to multiply this density with the area around that point. So in other words, without going into too many details, let's say this is the surface in question. If we take the parameter domain, right, this is d, let's say, and we split it into a partition, like we did for the double integral, each piece on the partition is going to correspond to a patch, right, on the surface. And then remember, by ds, capital S, we used to denote the area of that patch. And based on what we talked about previously, remember this is basically computed via the magnitude of the cross product of Ru and Rv. Why? Because Ru and Rv as vectors, so partial u, partial v of R, form a parallelogram whose area is the magnitude of the cross product of these two vectors, and that's going to basically approximate the area of that patch. To be more precise, this would be basically Ru cross Rv dA, right? I mean, if you follow the notation from the previous section. Now, if I want to find the mass at this point, I'm going to multiply the density times the area, assuming, of course, the density is given as a unit of mass over unit of area. So by that, we mean with this, basically with this remark, or with this motivation, if you want, the surface integral of f of xyz on S is denoted by, we're going to use the double integral symbol over S, the domain. So this S indicates that this is a surface integral, and then the function to integrate f of xyz ds, this is the formal notation, and then the way to compute it is via a double integral over the parameter domain with a function evaluated at the components of the surface and then multiplied by the cross product of RU and RB. Okay, so let's actually focus on this a little bit, because once again, there is a little bit of room for confusion here with the notation when we look at the double integral versus the surface integral. Okay, so the surface integral over a scalar field, the formal notation still uses two integral symbols because it's still an entity of dimension 2. I mean, that's the main reason for using the same notation for as for the double integral. Basically, the only difference is that the double integral is going to be evaluated over a flat domain, right, in the xy plane, right? When shall I say in the UV plane in this case, the parameter domain, whereas the surface integral, the function is evaluated on a generic surface S. So in order to not get confused with the formal notations of these integrals, what is the dead giveaway that this is a surface integral? So the two integral symbols and also the S, the notation coming from a surface, and also the most important piece that indicates this is indeed a surface integral is that you actually integrate a function of 3 variables, right? The double integral is for a function of 2 variables. So although we use the same symbol because the domain of integration is still 2-dimensional, the fact that we integrate a function of 3 variables, it's the clear sign that that's a surface integral. However, the way we compute the surface integral is still via an old-fashioned double integral. A double integral over the parameter domain. So in a nutshell, basically you plug in the surface into the function and then multiply by the magnitude of RU cross RV. It's analogous to what you did in the line integral. You plugged in the parameterization of the curve into the function to integrate and then multiply by the magnitude of the tangent in that case, in the case of a line integral, whereas here you multiply by the magnitude of a cross product. So try not to overcomplicate these things. The notation seems fancier than it is, than it would. I mean, it indicates basically the notation would seem to indicate a much more sophisticated approach or operation. But all you do basically you plug in the components of the surface into the function, perform this multiplication, and then simplify and obviously then solve the double integral. The common mistake, room for common mistakes is when you do this substitution of the surface into the function, as I'll show you in a moment, which is the reason you have to take your time to set up the integral carefully. So let's go over an example. Let's say I want to find the surface integral of xyz ds, in which the surface S is, let's see, I'm going to make this a little bit, let's see, I'm trying to figure out if I want to make it slightly more sophisticated. Yeah, I mean, not sophisticated, just to make it a little bit not as direct, you know, so we can have all the elements you may see in problems like this. Let's say the surface, so in other words, I'm not going to give you the parameterization yet. Let's say the surface is given by the paraboloid z equals you know what, I'll take that back. we'll get to examples like this before. So let's give the surface in the parametric format to begin with. R of uv with the components u cosine of v, u sine of v, and then u, with the parameter domain D given by a rectangle, essentially, u between 0 and 1, and v between 0 and pi over 2. I was hesitating how to give this, because if you actually write this surface in Cartesian coordinates, you will see it's actually a paraboloid. I mean, if you square x squared, y squared, and add them up, you're going to get y squared, u squared, sorry, not a paraboloid, sorry, a cone, basically. So the relationship between x, y, and z on this surface is actually z squared equals x squared plus y squared. I'll get back to that in a moment, because this shows you that when you choose actually the parametrization for a curve, you got to be careful and make sure you choose the one that is actually advantageous and not the one that actually makes your computation harder. But let's get back to the setup of the double integral. So once again, this is the surface, this is the parameter domain, u between 0 and 1, v between 0 and pi over 2. And before we set up the integral, I'm going to need the partial u partial v and the cross product between them. So partial u of r is 1 times cosine of v. Partial u of the second component is sine of v. And then partial u of the last component is 1. Rv, then partial v now is going to be minus u sine of v, u cosine of v, and partial v of the last component is actually 0. Let's perform the cross product. So Ru cross Rv. First component sine v times 0 minus u cosine of v. Second component cosine v times 0 minus, let's see, what do we get here? So the second component 0 minus negative u sine of v, and with another negative from the cross product, that's going to be minus u sine of v. And then the last component is u cosine squared v plus, because it's minus minus, plus u sine squared v. We really have to be diligent here and be careful with the algebra, because obviously we will make the integral much harder if we don't simplify carefully. So minus u cosine of v minus u sine of v. And notice on the last component, if I pull out u, cosine squared plus sine squared turns into 1. And so Ru cross Rv is going to be this vector. In the actual integral, we're going to have the magnitude of it. You can compute this inside the integral or separately like I did it here. So that's square root of u squared cosine squared v plus u squared sine squared v plus u squared. Again, the first two terms combine into u squared, which this makes it 2u squared. And then in the end, because u is positive, right, in our domain, the cross product Ru cross Rv ends up being u square root of 2. Okay, so let's set up the double integral as a, the surface integral as a double integral in the parameter domain. And we're going to decide later how to solve this. And now pay attention, this is the part where people make mistakes, but we'll get to that, like I said, I mean, with other examples as well. I mean, this is actually, when we do move on to surface integrals over vector fields, that's when you have even more room for mistakes if you misplace the substitution here. So go back to the surface, to the parametric representation of the surface. X, Y, and Z will be replaced by u cosine v, u sine v, and u respectively, right? So you go back to the function to integrate, x, y, z in this case, and just carefully replace u with cosine v, y with u sine of v, z with u, and then times the magnitude of RU cross RU, which we just determined before, which is U square root of 2 dA. Now, because the domain of integration is a rectangle, we can integrate in any order we want. For example, with U on the outside and V on the inside. And let's actually simplify this. We have U times 4 times, so you have U to the power 4, sine of V, cosine of V. There's also a square root of 2, which I can put it out, and then a d V du. Because this is the product of functions in U and V, this splits into a product of integrals, and because we have constant bounds as well. And the second integral in V, there's a U substitution you can perform here. I'm going to use a different variable, let's say y sine of V, dy is cosine of V dV. So I hope it's clear that actually you get 1/2 sine squared when you do that substitution. So this will be root 2 1/5 U to the 5th between 0 and 1, 1/2 sine squared of V between 0 and pi over 2. And then we get root 2 1/5 1/2 sine squared pi over 2 is 1, sine of 0 is 0, and then the final answer is root 2 over 10. So in a nutshell, this is the surface integral over scalar fields. Like I said, most of the real-life applications involving this type of integral is when you integrate density-like functions, in which it makes sense to multiply essentially the element of the area with the function evaluated at that point around the near a point on the surface. And surface integral is computed via double integral. Okay, that's going to be true also for the 1 over vector fields, which we're going to do next on the second page. So stay tuned. All right, so how do we integrate a vector field, right? Or over a surface? I should say surface integral of vector fields, right, over a surface, just like before, given by parametrization. So the main ingredients, let's again sketch that generic surface here. We'll get back to that in a moment. And so let's say that now we have a vector field in 3D with the components P of XYZ, Q of XYZ, and R of XYZ. Just like before, the surface is identified by a parametrization X of UV, Y of UV, Z of UV, with U and V in some parameter domain D. So the meaning of, if you use the analogy, like I told you before, the default example you should have in mind when you think about a vector field is a force field or a fluid. Even better in this case, let's say we have a velocity field in a fluid. So the meaning of big F of the vector field is, let's say, the water that flows in a volume in a certain region of space. Imagine that this surface we're talking about here is a net, or let's say a surface in general that allows the water to go through, like a permeable surface. And you want to know, so basically as a motivation or the default example, we want to know how much of F of this fluid goes from one side to the other. And so automatically notice that I need to talk about orientable surfaces. So we define this surface integral of vector fields using orientable surfaces. In other words, surfaces for which there is a meaning to the word from one side to the other. And remember the discussion, like for example, if you take the Mobius strip as a whole, there is no clear, I mean, there's no mathematical, there are no two sides essentially. So from one side to another doesn't make any sense. That being said, keep in mind that if I cut a piece of the Mobius strip, that's no longer a Mobius strip, right? I mean, that's going to be just an orientable surface with clearly two sides. So as a whole, the Mobius strip, the whole loop is non-orientable. But if we have, like I said, two clear sides, so if we can orient the surface, we can define a surface integral which will measure this flux, if you want, right? This is the flux across surface. That's another way of putting it. So let's say from our perspective, the way we see the surface, we want the flux going through from below to above, right? Now notice you will see in lots of problems this type of wording, find a surface integral oriented upward or oriented to the left or to the right or downward. This is because knowing a little bit about the geometry of the object, so let's say for example, we look at the surface and it makes sense basically to view it as top to bottom, right? And then if that's the case, then you can talk about the top side of the surface and the bottom side. So don't get confused with this wording in the sense that, I mean, once you sketch the picture, the surface, or you have an idea how it looks like, using Maple maybe, if it's hard to sketch, it should be clear what the problem is all about. I mean, what they mean by oriented upward, downward, outward, and so on and so forth. Okay, so going back to this one, upward from our perspective, it means that, again, if we do the partition over the parameter domain, we look at that typical patch that corresponds to each element on the partition. We're going to compute a unit normal. That's going to be with a cross product, if you remember, but we're going to compute it in such a way that the normal is oriented this way. So basically, in other words, when you do the surface integral for a vector field, you have to be careful how you compute the order of the cross products, RU cross RV or RV cross RU, basically, so that you make sure that the orientation is the one that you want in the problem. Okay, so we want to know how much of the vector fluid flows across this normal, this unit normal. So again, let the N is the unit normal. And remember, we'll get to that in a moment. Remember in this case, because this patch corresponds to a partition in the parameter domain, the partition in the parameter domain corresponding to du and dv, which leads to those tangent vectors ru and rv. Basically, the unit normal in our problem here is in fact ru cross rv divided by the magnitude of ru cross rv. That's the unit normal. Again, whether it's RU cross RV or RV cross RU, it depends on the parameterization and on the orientation that you desire on the problem. It's either that or the opposite of that. Now, don't get confused with whether the final answer is positive or negative. The overall flux across the surface is positive if I have a net flow from below to above, but it's going to be negative if the net flow is actually the other way around. So even though you compute, let's say, the flow across this normal, it's possible that the vector field, more of it goes against the way you pick the normal than in the direction of the normal. So therefore, the answer to the surface integral here, like with any integral, could be 0 positive or negative, right? It depends on the configuration of the vector field. But you still need to make sure that your orientation is correct so that you measure it in the correct sense. That's actually important in real life applications, right? You don't want to conclude, for example, you have an net outflow when in reality is a net inflow and you made a mistake just by picking the wrong orientation of the normal. Okay, so without digressing any further, let's go back to our discussion here on how we set up the integral. Let's say around this point where the patch is actually computed, let's say the vector field goes like this. So notice that in general, only a component of the vector field, of that vector f, will be straight across the surface across the normal. So in other words, what I want to integrate is going to be the projection of the, let me do this with the red color here. I want the projection of that vector field along the unit normal in this case. So because if you look at the angle, let's say the angle between these two vectors is actually equal to theta. What I want to integrate is the magnitude of f cosine of theta, right? Because the projection of f onto the unit normal, that's going to be an adjacent side to in that right triangle. So that's what you want to integrate. Now remember, from the cosine, from the formula of the cosine angle between two vectors, in this case theta is made of f and n. Cosine of theta is nothing but f dot n divided by the magnitude of f times the magnitude of n. Okay, so I forgot to mention something. What we want to integrate is the amount of fluid of the component of f along the normal multiplied by the area of the patch, so multiplied by ds. Because again, think of it as a flux, which basically tells you how much it flows per unit of surface, right? I mean, that'll be the meaning, for example, of f of x, y, z. All right, so that's what we want to integrate. Once again, the first two components in these expressions will be the projection of f onto the unit normal, and then times the area of the patch. Okay, now because the normal is, like the name implies, it's a unit normal, obviously the magnitude of n is going to be 1. So this can cancels, the magnitude of f cancels as well. And let's actually replace now n with the formula for the unit normal. So let me actually do it in two stages here. So basically what we integrate is f dot n multiplied by the area of the patch. This is the reason why in the formal notation you will see this type of writing when you define formally the surface integral over vector fields. But then when you evaluate to see what that is actually equal to, when you evaluate it on the surface itself, that's the moment when you actually plug in the components of the surface onto the vector field. The unit normal is in fact Ru cross Rv divided by the magnitude of Ru cross Rv. So that's a dot product. And on the outside, ds, remember, is the area of that patch, which is the magnitude of Ru cross Rv, the area of the parallelogram. And this cancels as well. So when everything is said and done, the surface integral, we're going to write it on the next page in a minute, of a vector field, which has this formal notation. There is another alternative notation. Let me put it here as well. F dot ds bar on the top to indicate it's a dot product with a cross product representing that parallelogram. Is going to be the double integral over the parameter domain, where of f of r of uv dot ru cross rv, or rv cross ru, depending on the orientation that you pick. Okay, so let's compare with the surface integral of scalar fields, right? So if you integrate a scalar field, kind of the same idea, you're going to evaluate the scalar field at the components of the surface, but then you multiply by the magnitude of the cross product of Ru and Rv. It's still a double integral. Whereas in the case of vector fields, over here, we have the dot product between vector field evaluated at the R of uv, which is going to be a vector in itself, and then the cross product between Ru and Rv. So I hope that's clear how it's set up. Let's move on to go over a couple of examples on the next page. All right, so let's do an example. Let's evaluate the surface integral over a vector field as follows. So f of x, y, z is given by the components, let's say x, y, z squared, in which, and let's make it a little bit more complicated, in which s is the cone z squared equals x squared plus y squared. Let me think a little bit. In the let me think a little bit. How do I make it? Let's say in the positive region. So let's say S is the cone corresponding to x greater than 0, y greater than 0, and I want also z between 0 and 1. So it's actually a portion of a cone and oriented let me think a little bit, downward. Okay, so if I were to sketch this cone, let's see if we could do a little sketch here. It's going to live in the positive region, like I said, of the space. And kind of like this. Let's see if we can do it. Okay, so imagine this is actually flat here, flush here over the... So it's basically connecting these 2 points on the xz and then on the zy plane. Let me see if I define it correctly, right? So x greater than 0, y greater than 0, and then z between 0 and 1. Okay, so this is the surface. So it's like I want to know how much of this vector field goes through the cone, but from the inside to the outside, oriented downward. And I mentioned downward because I want basically the flow to be measured this way. And if I compute the normal, if I pick any point on the normal, see, that's why you need to know the geometry a little bit of the object. Any normal that points kind of outward, so outside of the cone, if that's what I want, the direction of the flow to be computed via this surface integral, basically all these normals will have negative z component, just because of the shape of the cone, right? And if you look at the normal, then all of them will have a negative z component. So basically, when I compute Ru cross Rv, or Rv cross Ru, once I pick a parametrization, I'm going to pick the one with negative z component. It's as simple as that, basically. I mean, just compute the cross product in any order you want. Most of the time you kind of tell, actually, because you will see the parameters sometimes are x and y, and then given the shape of the object, it's kind of clear that that's the order of the cross product. But I really insist on not guessing, because it's kind of, having bad learning habits if you do that. Sometimes people say, oh, I mean, I'm going to check the answer. If the answer is the negative of the integral I get, that means I choose the orientation the opposite way. No biggie, I'm going to change the sign. But in real life, you won't know the answer, basically. And you won't know if the correct answer is negative or positive. Okay, so you still have to pick the correct orientation. Okay, so let's move on now to the surface itself. We need a parametrization. See, this is another time or a place in which you have to think carefully how you choose the parametrization. We used this surface before, and you already know there are different types of parametrization. So if nothing comes to mind, no parametrization comes to mind that is obvious or clever, let's say, you can choose, for example, one option. You can choose, for example, to say, I'm going to have x to be u, y to be v, and then from the equation of the cone, then z is going to be square root of u squared plus v squared. But this time might not be ideal, if you expect, for example, some terms to be complicated. And it might be difficult to know beforehand, but I kind of tell already that it might be difficult, right? Remember, in the surface integral, I'm going to have to come up with partial u partial v. So if I take partial u of the radical, I'm going to end up with, like 2u over, 1u over square root of this. So you're going to have the square root of the denominator. Could be a difficult endeavor, right, to deal with that. Another better parameterization is via basically cylindrical coordinates, right? I mean, you keep one of the parameters to be the third coordinate. You can call it z. I mean, you can exploit the fact that in terms of x and y, so in terms of x and y, I can choose polar coordinates, basically. Right? Why? Because the cross section of this cone is a circle, right? For a fixed z, I can take x and y to be as in terms of polar coordinates with respect to z. So in other words, I can think of x to be z cosine of theta, y z sine of theta. And then furthermore, to use u and v, so we can use the same traditional notation so far, that suggests that it, so I'm going to use actually u and v instead of z and theta. Let's then move on to choose, like I said, to choose z to be actually u, and then choose x to be u cosine of v, and then y to be u sine of v. You can leave z and theta if you're comfortable, but again, just to use the standard notation we used in this sections, let's use the u and v as well. Therefore, my surface in the parametric format, r of uv, is now u cosine of v. We had that before, right, in the previous page. U sine of v, and then u for z. Now, what does the parameter domain become at this point? Well, the parameter domain is going to be u between 0 and 1. That's the previous z. And because it's a quarter of a circle, right, if we project this onto the xy plane, we get the quarter of a circle of radius 1. That's going to be 0 pi over 2 all the way around the circle. So v is between 0 and pi over 2. So for a given z, you go a quarter of a circle. So that is now the parameter domain. All right, so I hope you appreciate that I insist on this. I mean, I purposely go slow before I actually tackle the integral, because in problems like this with surface integrals, you have to be careful to make your setup correctly. Okay, so I think we have everything we need. Let's set up the surface integral. According to the definition, this is the double integral of f of r of uv dot ru cross rv. Actually, so that's the definition. So we're going to need ru and rv and their cross product. So let's take a step back and do the cross product, right? So ru, so first of all, we have partial u. We're looking at the parameterization of the curve very carefully, right? So partial u is going to be 1 times cosine of v. We did this actually before, right? U 1 times sine of v, and then 1. Rv, once again, is minus u sine of v, u cosine of v, and then 0. So we did it before. And then ru cross rv is going to be minus u cosine of v, followed by minus u sine of v, and then u, right, after you make that simplification. Okay, so here comes the part that it's easy to mess up if you make the substitution incorrectly. So what is f of r of uv? Go all the way back to the top of the page and look at the vector field. Okay, each x, y, and z is going to be replaced by whatever x, y, and z is on the surface. So I'm going to actually indicate here with a red color on the surface. So this is x, this is what we're going to replace x with, this is what we're going to replace y with, and this is z, right? Z equals u. All right, so f of r of uv is going to be x, which is now u cosine of v, y, which is u sine of v, and then u, which is z squared, which is u squared. And then you dot product this with ru cos rv, which is minus u cosine of v minus u sine of v, and then u. So we perform the dot product, and then we compute the double integral that results from this. Dot product is minus u squared cosine squared v minus u squared sine squared v plus u to the power 3 dA. Pull the negative u squared and then perform another simplification, and actually ends up double integral of minus u squared plus u third dA. Once you simplify, now you worry about how to compute the double integral, which in this case is pretty straightforward. Bounds are constant. And this splits into a product of integral from 0 to 1 of 1 dv, 0 to pi over 2, right? 1 times dv. And then the integral from 0 to 1 of u third minus u squared. Moving on, so that's going to be v between 0 and pi over 2, which is just pi over 2, and then 1/4 u to the 4th minus 1/3 u to the 3, 0, 1. We get 3 minus 4, which is negative 1, minus pi over 24. Okay, so let's interpret this. We're going to do another example on the next page, but let's again make sure we understand the meaning of this entire thing. Despite the fact that I indicated this normal pointing outward from the that cone, it turns out that in fact I have a net inflow. So for example, imagine this vector fluid or vector field is all over the place. And until we actually do the surface integral, we have no idea if more water comes outside of the cone or inside of the cone, right? Imagine the cone is actually a permeable surface. So the surface integral tells us the answer. There is a net flow, inflow equal to this. Why is it inflow? Because it's negative. It means that the net flow, it is against the direction of the orientation that you perform, right? So you want to know how much water comes from the inside of the cone to the outside of the cone. The answer is not only not much comes in, actually more comes in than out of the cone. Okay, the ship is sinking, in other words. All right, so let's move on to another example. All right, so let's do another example, and then we can call it a day. The vector field, this one we're going to do it only partially. We're going to just set it up primarily, and then the last integral I'll just give you the answer, because I want to focus primarily on the setup, which is the main issue most of the time. So let's say the vector field is given by the components yz, zx, xy. The surface is given by z equals x sine of y, with x between 0 and 2, and then y between 0 and pi. And I want this to be oriented upward. So when it says oriented upward, again, it means that positive z. Now, we don't need to sketch anything essentially in this case, because the problem basically tells us everything we need to know. Probably if we were to sketch the surface, it makes sense to call the one side the upward side and the downward side. Again, it all depends on how the surface looks like from your perspective, right? I mean, if you are aligned parallel to the z-axis and you see it like that, then upward means positive z. That's the meaning of it. And the domain is already given, the parameter domain. I mean, we didn't establish the parameters yet, but because the way the domain is given, it makes sense and to actually choose the parameters u and v to be x and y. That's, you know, the logical thing to do, and probably there is no better way to go about it. So the same surface then in the parametric form is going to be u for x, v for y, so automatically z becomes u sine of v. You can work with in terms of x, y, and z, but I find it, at least in the beginning, to stick to this alternative notation to clearly emphasize which are the two parameters for the surface. But make sure you also change the notation in the parameter domain as well. So now u is between 0 and 2, and then v between 0 and pi. So what is the surface integral? Again, according to the definition, that's f of r of uv dot ru cross rv. But I have to make sure that, like I said, the z component is positive. Otherwise, else we're going to write rv cross ru. So let's see what we get for ru. Partial u is going to be 1, 0, 1 times sine of v. Rv is 0, 1 u cosine of v. The cross product now, ru cross rv, then it's going to be 0 minus sine of v. The middle component, 1 times u cosine of v with the negative sign, minus u cosine of v. And as you can see here, the last component is 1. So you see, typically, you know, when x and y are your parameters, when you do the cross product in this order, u and v is the world x and y, right? Automatically you have 1, the last component. So it's positive, so it's oriented upward. The other way around is going to be negative, right? If the parameterization is all different, so it's not intuitive like this one, you're going to have to pick a test point, basically, and then make sure that the normal is in the orientation that you want. Okay, so let's focus now on the substitution. So go back to the parameterization of the surface. You're going to replace u with x, v with y, z with u sine of v into the vector field. So now this double integral becomes of yz, which is now uv sine of v, zx becomes u squared sine of v, xy is u times v, and then this is dot product with ru cross rv, which is minus sine v minus u cosine v 1 dA. And let's see what we get in the cross product. In the dot product, sorry, we get minus uv sine squared minus u third sine v cosine v, and then plus uv. Constant bounds, let's do, I think the easiest thing is just to do the integral in u first, and the integral in v, which results from this, I'm going to provide it to you, but I mean, I'm going to give you the integral, but I'm not going to go over all the steps because it's it's rather tedious. So let's put the integral in v on the outside, which is from 0 to pi, and let's do first the integral from 0 to 1 of this. What did I say? Du first. 0 to 2, right? The domain is 0 to 2 for u. So du first and then dv. Okay, so v is a constant, so let's follow the v is a constant right now with respect to u. So this is 1/2 u squared. The next term, the integral of that will be minus sine v cosine v 1/4 u to the power 4, and then v 1/2 u squared with u between 0 and 2, and then dv at the end. Okay, so if I plug in 2, I end up with the following. 2 squared over 2, that's 2, so it's going to be minus 2v sine squared v, and then 16 over 4, that's 4. The middle one is minus 4 sine of v cosine of v, and then plus 2v. Okay, so the last two terms are immediate, right? I mean, this is v squared, the antiderivative, right? This goes into, this is a u substitution, it's sine squared v over 2, so that turns into minus 2 sine squared v. This is rather tedious. I mean, you're going to have to use the fact that sine squared v is actually 1 minus cosine of 2v over 2. So the double angle formula. One second. Cosine 2v minus 2 sine squared. Okay. All right. So the double angle formula for sine squared v, but then it's going to be v times the whole thing, right? Okay. So you're going to have to use by parts. Okay. So integration by parts is rather tedious piece here. But all in all, the antiderivative should be, for the first term, you will end up with minus 1/2 v squared, 1/2 v sine of 2v plus 1/4 cosine of 2v. That's the first piece. And like I said, the other ones are minus 2 sine squared v plus v squared. Anyway, take the time and evaluate. This is between... right, all this is between v0 and v pi, right? So when you evaluate that, the final answer should simplify to pi squared over 2. So that's it for the surface integral. Just to anticipate the last topic, we're going to go over two major theorems, which are versions of the fundamental theorem of calculus, the so-called Stokes theorem and the divergence theorem. Both of them involve line integrals, surface integrals, triple integrals, lots of different topics that all come together. They have important physical meanings. The Stokes theorem is essentially a generalization of the Green's theorem in 3D. And the divergence theorem concerns surface integrals for closed surfaces. Like, for example, a sphere or an ellipsoid and stuff like that. Okay, so that's it for today. We'll meet each other next time.